A very good afternoon to you all. Welcome to this week's Coloquio. We'll be hearing from our own Eric Jiménez today. So a little intro about Eric. So Eric did his master's from the National Institute for Astrophysics, Optics, Electronics in Mexico. Then he went to Bonn, Germany to obtain his PhD at the International Max Planck Research School. And later on, he went to do a postdoctoral fellow at the NRAO, that is the National Radio Astronomy Observatory in the US. And then he's joined our institute in 2022. Eric is mostly, well, his biggest interest is in the field of galaxy formation and evolution. He makes use of VLA data, ALMA, and HST to complement his investigations on how stars are forming and how black hole activity shapes our galaxies across cosmic time. And today we'll hear more about that from his talk. Thank you, Eric.
Thanks a lot for the introduction. So, yeah, I will give you an update about the things we have been doing with these deep extragalactic surveys that we have obtained in the past years. Yes. Okay, so this is the outline of the talk. I will begin by giving a general introduction to extragalactic radio surveys. Then I will jump to the motivations. I will try to explain why we need different high-resolution radio surveys. I will present the 3 radio surveys that we have been working on. And I will use this data to test if radio continuum emission is a reliable tracer of star formation at high redshift. I will present observational constraints of the so-called little red dots at high redshift. And finally, I will show some nice figures, not only dots. Okay, let's begin. I always start with this figure because it clearly illustrates why we need deep and large galaxy surveys, because this allows us to get large compilations of galaxies at different redshift or cosmic epochs, so that we can try to understand how we went from these high redshift galaxies, these fuzzy low mass galaxies, to the complex and massive, well-structured galaxies in the local universe, like the Milky Way. So now we have a general picture about how these processes went. We know that the first galaxies, that the galaxies in general, formed within the first billion years after the Big Bang, and they continue to grow throughout the remaining cosmic time. But the exact mechanisms that regulate the production of stars and therefore the growth of galaxies are still being addressed. Okay, if you want to study star formation, and this is particularly for grad students, we can use different wavelengths. So you know that we can use the optical, we can use optical lines, alpha, whatever. We can use the UV because then we can trace the emission from massive stars. At the same time, we can use infrared because we can trace the thermal emission from those particles that are being hit by the massive stars. And also we can use radio continuum emission because we can trace synchrotron from supernova remnants and free emission from H2 And the clear advantage of infrared and radio is that these are they allow us to get dust-unbiased probe of star formation. And this is particularly relevant for the high redshift universe because most of the production of stars have remained obscured by dust. So here you can see the cosmic star formation rate density of the universe. In other words, this is the number of new stars per year per commodity volume as a function of the redshift. And you can see here the contribution of the star formation that is being obscured by dust and the one that can escape from the dust. And up to redshift 4, you can see that, as I said, most of the star formation has been embedded in dust. Now, if you want to get spatially resolved information about these galaxies, what we need is high angular resolution. Then we need high resolution, so interferometric observation that can be done with radio, millimeter interferometers like ALMA, VLA, and so on. Motivated by this, a lot of surveys have been carried out, especially at low frequencies, because at low frequencies, you know that we have a larger field of view or a larger primary beam for astronomers. At the same time, given the spectral shape of typical star-forming galaxy that goes like this, we expect higher flux densities at lower frequencies. Some key surveys that have been obtained in radio. This is the Cosmos 3 GHz map that covers these 2 square degrees here. And this is still, after 10 years, this is still one of the largest and deepest. So it had a resolution of 0.25 arcseconds, 25, and RMS of 2.3 microjansky per beam. And we also have the VLA frontier field survey that targets 3 massive clusters. So the idea is to leverage the power of gravitational lensing to detect galaxies that are behind the cluster, so that we can detect galaxies that are either very faint or at high redshift. And similar to the 3 GHz surveys, we have a 0.6 arcsecond resolution, RMS of 1 microjansky per beam. So some of the key results from these surveys is that, as I mentioned before, we are able to better constrain the evolution of the cosmic star formation rate density of the universe. And also, because we are able to detect radio-loud AGN, we can trace the evolution of the number density of radio-loud AGN as a function of the redshift. And you have seen probably this before, that these two evolutions are quite similar. We see that there is an increase in the cosmic star formation rate density out to redshift 2, and at the same time in the number density of AGN. This is likely because we have a growing dark matter halos at high redshift that they haven't had enough time to get a lot of gas and produce a lot of stars, and therefore, and at the same time to fuel an AGN. Then you have a peak at redshift 2, and then because you have consumed all the gas, then you will not be able to sustain the production of stars, and at the same time, well, you don't have food for the AGN. So this suggests that galaxies and the supermassive black holes will evolve. So this is due to what we call the AGN feedback mechanism. In particular, the way that this AGN feedback works in galaxies could be via the radio mode feedback. So again, for grad students, just to remind you, radio mode feedback is when you have relativistic jets that inject a lot of energy into the ISM so that they heat the gas, and therefore it cannot cool, and then we cannot form new stars. We have found evidence for that. So in this paper, here you can see excess of star formation, or for those who work in extragalactic astronomy. So this is distance to the mean sequence. So higher values are higher star formation rate with respect to the average population of galaxies as a function of the stellar mass. And the contours show the distribution of radio-selected star-forming galaxies.
Can you repeat again?
This value, excess of star formation?
Yeah.
Excess of star formation, or distance to the mean sequence, is the star formation rate of a galaxy divided by the star formation rate of a galaxy on the main sequence at the same stellar mass. So if you have a higher value, means that you have like 10, this is a logarithmic scale, 10 or 100 more higher star formation rates than the typical population of galaxies. So in color, you see the symbols that show radio galaxies, F1, F2, hybrid morphologies, and also compact AGN. And what we found is that radio-loud AGN tend to be at higher stellar masses, and also they are in the green and red region of this diagram, which suggests that radio mode AGN feedback is helping to suppress or maintain the low star formation rates of these galaxies, and at some point these galaxies will be quenched.
What do you call it? Radio mode quenching?
It's because you have like the injection of energy due to the jet, the relativistic jet that can hit the ISM. The other mode is the quasar mode or radiative mode, but that's related to the radiation of quasars, like typical quasars, not related to the jet. It's
and the jet is related, somehow connected to the radio?
Yeah.
Okay.
So they have jets. I mean, they are related?
Yes, but I mean, in terms of the definition of what we call, it's a weird terminology. So let's say that the radio mode AGM feedback, you do have a jet, and the jet dominates the input of energy with respect to the energy that is released by radiation. So you can have both, but the one that is dominant is the one from the jet.
Is that the one called the jet feedback? Is that the same?
Yeah.
I'm sorry, I never heard it. EGM feedback.
Yeah. It's you can find like.
Okay.
All right. Okay.
So, just to.
Yeah.
So one is radio mode quenching, and the other one is what's?
Radiative.
Radiative. Okay.
It's a bit confusing. So the other thing that we can do is what I did for my PhD project. This is the main project of my PhD, which is we try to relate the structural properties in radio of galaxies with their star formation rate. Here you can see again excess of star formation or distance to the mean sequence as a function of, extent of star formation. So this is the size in radio as a function of excess of star formation. So again, higher values imply that you have a higher star formation rate with respect to the average population. And this is the selection function, the blue line, and this is the density distribution of galaxies, and these are like median average properties per star formation technique. What we can see here is that galaxies on the main sequence, so typical galaxies on the main sequence, are preferentially extended, while star-forming galaxies or stable galaxies are are always compact. So, which is something that you can see here, right? So, all of this is helping to define this consensus of the structural evolution of massive star-forming galaxies with time and stellar mass. And to exemplify that, here you can see excess of star formation. This is the diagram from Sandro Tacella in 2016. So again, excess of star formation as a function of stellar mass. And as you know, the galaxy will accrete gas from the cosmic web. They will form stars. But eventually, once you have a strong gas inflows or mergers that led to a strong episode of star formation in the central part of the galaxy, you have like this so-called compaction. But once the gas is depleted, the star formation rate will decrease and it will repeat the cycle. But eventually, the replenishing time will be larger than the depletion time, so that you will not have gas to continue the production of stars. And that's when you start to move to the green valley, and eventually you are quenched. And this is what we are finding in these two separate studies. So in one, you see that indeed we see this compaction effect, that you become compact and you have a high star formation rate. We also find this population of galaxies that are compact but do not have a high star formation rate. And at the same time, we're finding a higher fraction of radio lobe AGN in the green valley.
Sorry.
Yes?
What do the arrows say on the blue and the red arrows? I cannot.
Compaction and depletion.
Oh.
An end is missing.
Oh.
Okay. Yeah.
In this plot, if there is no more gas coming in and then you quench the formation, why the stellar mass is increasing still?
Well, it's not that you don't have the gas content drops abruptly. So this is just like okay, you don't have enough gas to go back to increase the star formation rate, but you still form stars with the gas that remains. Let's put it that way. Yeah.
You could also accrete the stars by emergence.
Yes, also that. Yeah. Okay, so this is all for the introduction. Now we move to why we need deeper and higher resolution radio surveys, and I think I need to speak quicker. So the motivation can be summarized in this slide. So you see that this is a simulation of a galaxy at redshift 1.2 with an angular resolution of 1.2, 1.05 arcseconds, which exemplifies what we can get with most of the current facilities, so essentially a lot. This is the best that we can get with the VLA. And you see that we start to see some structural properties. And hopefully someday we will see something like this. This is like the imaging quality that we will get with the SKA and VLA. So I think that the motivation is clear here. So we want to go from blobs to something that we can start to resolve here. But not only that, we also need sensitivity. This plot is from 10 years ago, from the paper from Vanessa Smolchik and the Cosmos 3 GHz survey. This is sensitivity as a function of the area. And with this sensitivity, so this was the deepest map that we had at the time, we were able to detect galaxies, mean-sequence galaxies with a characteristic stellar mass 10 to the 10.5, out to redshift around 1. This is star formation rate as a function of the redshift. This is the star formation rate of a typical galaxy on the mean-sequence with different stellar mass. But we were missing a critical epoch in the universe, which is the cosmic noon. So you remember the peak of the number density of radial log AEM, and also of the peak of the cosmic star formation rate density. So we need to go deeper. And the surveys that I will be presenting are able to prove that regime. Okay. Now, this motivated this BLA survey of the GOODS-N field. This is the first high-resolution, high-frequency observational campaign that maps and entices extragalactic field, because we needed a lot of time. It was a large program of the BLA. And large program, like 360 hours to only detect 256 radio sources. And you can see here the diversity of sources. They are like, yeah, we still have some X, but we have some spatially resolved information. Now, if we were to compare the sensitivity of these new radio surveys, well, relatively new, this is RMS noise as a function of the area. You can see that we are going deep. This is past, present, and future radio surveys. And in terms of resolution, you can see that the resolution is only comparable to a small fraction of the whole deep field, and this required like very long baseline interferometry. And this is the type of things that we can get. This highlights why we need radio emission, because you can see that if we only have HST UV imaging, we will be missing the part of the star formation that is being obscured by those. But also we obtained 3 GHz maps of the EGS and the GOODS-N field. These are two premier fields of the James Webb. Why 3 GHz? Because as I said before, you expect higher flux densities and lower frequencies. And therefore you are able to get radio sources at higher redshifts. And at the same time, with the VLA, we still get sub-arcsecond angular resolution. This was not last program of the VLA. It was 64 hours, 120 hours to reach the sensitivity, 0.35 microjansky per beam, and sub-arcsecond resolution, and in total around 3,000 sources. This is again the same comparison, just to illustrate that we are going deeper than previous surveys. And in terms of resolution, well, this is the best we can get with the VLA. Okay, now, what can we do with these radio surveys? Right? So think that you are an astronomer and you have a big map, and the first thing you do is counting. You count your sources because it gives you an idea about the abundance of radio sources as a function of flux density. And you might be wondering, why this weird unit? These are Euclidean normalized source counts. Why? Because back in the 80s, smart people thought, okay, we want to see if there are some deviations of the universe with respect to the non-Euclidean universe static. And we know that the abundance of sources with respect to the flux density goes down with a slope of minus 2.5. So you multiply by that, you will expect to see like a flat line, right? So any deviations from that will indicate either deviations from the cosmic evolution or changing source population. So we derived the source counts of these surveys. And I will skip the weird, the boring part of this work, that is, you have to take into account a lot of corrections, but that's something for astronomers, I guess. So here you can see the abundance of radio sources as a function of the flux density. The data points from our surveys are the ones in red, for the two different fields. The continuous lines show the different predictions from semi-empirical models or simulations, and this red box shows predictions from an observational method called PD estimate, which are based on statistics about the noise of an image. So this is an indirect method to estimate the distribution of sources as a function of log density. All right, so what we can learn from this comparison is that we can tell if in numerical simulations, we could both be wrong, no? But we probably trust the observational results. Or not, I don't know. So there is a disagreement here. So the thing is that with this new data, we can prove like really faint sources, because most of the radio surveys have been limited to this part, right? So now we are able to put this data point here, and what we're finding is like there is a disagreement with some of the most accepted words to derive circles, like Bonaldi, which is a semi-empirical simulation. I want to understand why. So what we are seeing here.
But if you call those disagreements, other points might also be disagreement.
Yes, yes. So you mean that this point is in disagreement, not this. This point is disagreement with Bonaldi, this the blue line, but these red data points do not. Yeah, that's exactly what I want to say. That the only thing that not the only thing, but it seems that Bonaldi, it kind of reproduces all of them. Yeah, okay, here we have, but something that appears to be consistent in both cases here is that this data point is below expectations. But it's consistent with the other observational result, the indirect method. So we have two observational results, one all numerical simulations that, okay, this is semi-empirical, kind of makes sense because it's fully semi-empirical. But these two, the one in magenta and the one in blue, are above, right? So this suggests that somehow numerical simulations are over-predicting, or we are under-predicting the abundance of failure resources.
For those low flux density data points, how confident are you about the error estimates? And is there any systematic error you have?
We took into account all the errors about the corrections and everything. Yeah, that's kind of yeah.
And the theoretical lines, they don't have an error?
Okay. So the systematic error, that might be a
problem.
Okay, so you want to see why there is a disagreement with the observations and simulations for sources that are too faint. And what is the galaxy population that will be too faint? Well, galaxies that are at high redshift. So we took the T-Rex simulations to investigate the origin of this disagreement. And okay, let's say we caught all the galaxies that are above a given redshift, right? Above redshift 3.8, 2.6, 1.8, 1.3. And you see that indeed it brings this data point in better agreement with the resulting trends. But this also brings in disagreement the other data point. So it's not necessarily that high redshift galaxies are being over-predicted. But what other galaxy population can produce this type of effect? Low mass galaxies. It turns out that if we cut low mass galaxies from the simulations, it better reproduces our results. So you can see that if we were to exclude galaxies with halos lower than 10 to the 12 solar masses, we recover this sharp decline in the radio source counts. So this is in agreement with studies in the local universe that have shown that low mass galaxies tend to be radio dim. So here you can see 6 GHz flux density or luminosity as a function of the star formation rate, total star formation rate. And this is for little things, so low mass star forming galaxies, and you can see the comparison with more massive galaxies. And based on theoretical predictions, what theoretical people say that if you have a shallow gravitational potential, then the electrons that were supposed to produce synchrotron emission, they can escape from the galaxy halo. And if you don't have electrons to produce synchrotron emission, then you don't have enough synchrotron emission, right? And indeed, T-Rex tried to compensate for that, but what we are finding is that it seems that this radio emission, well, it needs to be revisited. These are the prescriptions that have been used to take into account that effect. Or we are messing up, I don't know. Now, with these radio maps, we can also explore these key questions. So let's be paranoid and think, okay, so we have been using local relations to derive star formation rates of high redshift using radio continuum emission. But what if the early universe had different conditions than in the present epoch? And that's not something like totally new. We know that the energy density of the universe scales as 1 plus c to the 4. So at high redshift, the universe was had a much denser and much energetic path of CMB photons. Why is that important? Because if you were to have like a galaxy at high redshift and you have here an electron and then it collides with a CMB photon, then you have inverse Compton scattering. And instead of this electron, if this electron was supposed to emit in synchrotron, then you lose that emission, right? And again, you have this beam effect in synchrotron. And motivated by this work, I was reading the archive and I realized that I was not invited, so all my gang was working on this and they didn't invite me. And I thought, okay, I can do that, because they reported this tentative evidence of inverse Compton scattering at high redshift. So this is what they did. So they took a large radio survey and they stacked maybe 200,000 high redshift galaxies, line-of-day galaxies. And for those who don't know, stacking is like what astrophotographers do. So you have like short exposures and then you take the average and then you increase the signal-to-noise ratio. So essentially what we do is that we look into the trash of someone else and we get some signs. And they were able to get this plot. So they say, let's plot the infrared luminosity divided by the 1.4 GHz radio luminosity. For those who know this is the infrared radio correlation. So in the local universe, we know that the factor of the ratio should be here, right? So in case of no inverse Compton losses, you will expect to see something like that, right? But they found that at high redshift, the radio luminosity is decreasing so that this ratio is going up, right? And when they plot the expected, theoretically predicted suppression of radio emission due to the inverse Compton scattering, well, you can see that it goes in the same direction, right? The thing is that they don't have, well, there are a lot of caveats, and one of them is that they don't have information about the dust properties. So this could be entirely biased. And that's when I say, ha, I do have that, and I will not invite you to this work. No, I mean, of course, Eric is here, Eric Murphy. So what I did was to select a sample of star-forming galaxies, because I do have the information about the stellar masses, the UV continuous slope. So I'm trying to limit your sample to those galaxies that have little to almost negligible dose obscuration or dose extinction. Then I applied a bootstrapping stacking analysis to derive the average radio luminosity in this plot. But in some cases, as you can see, we only have upper limit. But even with these upper limits, you can see that the radio luminosity seems to be declining with redshift. And is this expected? So how we can corroborate that? We know that in the local universe, we have a given radio luminosity. We have a radio luminosity for a given star formation rate, right? We do have star formation rates of our galaxies. So we derive the average star formation rate per redshift beam, and then we infer the radioluminosity predicted by local relation. And this is the one that is being predicted by local relation, the one in red, which is well above the observed values. Now, if you plot the expected decline in the radioluminosity due to CMB, inverse Compton of the CMB here, you see that, okay, it kind of goes in the same direction. But again, there are some caveats. So this could also point toward different physical processes, like you could have a top-heavy initial mass function or a different mass function, or radio spectral indices at high redshift could be different. That's something that we need to explore. And as I will mention then, there is something that we have to take into account, that is the dependence of the morphology, the radio morphology with frequency, which is the next section. So again, coming back to the local universe, we know that if you were to observe a galaxy at low frequencies, the morphology will appear more extended. So here you can see a comparison of local 145 megahertz compared to the 1.4 gigahertz from Westerprobe. Why is that? So we know that from, I would say, physics, that high frequency electrons, they lose their energy more rapidly, so the cooling time is shorter. So that if they die like soon, they cannot propagate a lot into the ISL. So that this led to differences in the morphology of galaxies at different frequencies. And at low redshift is kind of okay, like yeah, we know that, but should we worry about this when we try to study galaxies at high redshift? I think yes. Because imagine that you have a survey at 3 gigahertz. A galaxy at redshift 0, the emitted frequency will be 3 gigahertz, because you have like 1 plus C factor. But if your galaxy is at redshift, for example, 3, then what you're actually observing is not 3 gigahertz, but it's 10 gigahertz, right? So if you want to study the structural evolution of galaxies in radio, you have to take into account that effect, because otherwise you're proving, like, comparing apples with, I don't know, watermelon. And this is a plot that I used for a proposal, because I took, okay, let's see, right from the literature, we can see a trend. This is the radio size of massive stuff in galaxies redshift 1 to 2 as a function of the observed frequency. And this is like a bunch of works of different resolutions. But even with these different conditions, you start to see this trend, that at higher frequencies, you see more compact radio sizes. But we were not able to consistently and systematically prove this trend because we didn't have the maps to do so. That was until we got these 3 GHz, 10 GHz maps of GOODS-N and another team led by the British got the 1.4 GHz maps, all of them with sub-arcsecond resolution and reaching similar depths. And that's the first project of PhD project of Miguel Vega, who is now enjoying Paris. And he's finding this trend. So here you can see the radio size of galaxies as a function of emitted frequency. And once you compare with the expected trend from basic or standard cosmic ray propagation models, you can see that it doesn't fully account for that. So there might be another physical processes that are driving this dependence. One of them is okay. It could be redshift, so he tried to split, he did split the sample in 4 different redshift beams just to make sure that this trend remains nearly constant with redshift, so that this indicates that another physical mechanism internal to the galaxy might be driving this trend. But I don't want to spoil Miguel's results, so if you are interested in this, he will be talking about this in 2 weeks or 3, so don't miss out. Yeah.
Are you assuming the same intrinsic spectral index for
that's a key question, yeah.
And at high redshift, you don't get to the optical stick part?
Well, the thing is that he's taking into account the spectral indices to see. That's a very good question, because we thought, okay, maybe there is a correlation with the spectral indices will tell you something about the age, right? So you have a younger stardust, then it will look more compact. But he didn't. I'm spoiling his result. But yeah, he will explain in detail. Thanks for the question. Okay, so now let's talk about these fancy and weird sources called little red dots. So back in 2022, well, right after the launch of the James Webb, the community reported these extreme massive galaxies at very high redshift. It was like, everything was very, 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 and very rare. So why this was important? Because, you know, it's difficult to explain. I don't know what Bernardo has to say about this, but as far as I understand, it's difficult to reproduce very massive galaxies, again, in the early universe. But then it was shocking that wherever you see in the sky, you start to see these sources, these little red dots. This is the term coined by Jori Matti in his paper from 2023. And probably the most striking thing about little red dots is that they exhibit this broad H-alpha emission line up to 2,000 kilometers per second. And if you assume that these are powered by AGN accretion, this will imply supermassive black holes with masses of 10 to the 7, 10 to the 8. But also this could be explained by Gauss. Let's keep the line about the AGN for the moment. Okay, the community thought these are AGN. These are dust-embedded AGN, early AGN, so we should be detecting this in the X-ray. So that's what Roberto Maiolino and his team thought, and they went to the deepest X-ray, the ray images, and they found nothing. These were not detected. So here you can see volumetric luminosity divided by X-ray luminosity as a function of volumetric luminosity. These are the expected trend from like standard quasars. Here you can see local analogs. I will talk about this in a moment. But local analogs, they meant galaxies that are low redshift or in the local universe with low metallicity, low mass, but they also exhibit these broad H-alpha line profiles. And none of them are detected. And there is like 10 pages of discussion in that paper just to explain why they are not detecting, and they play with a lot of ideas like Compton thick or super Eddington accretion, or that the magnetic field is too weak because you haven't had time to form like a strong corona, whatever. And then I was in a meeting when they stole my computer, not this one, but in Portugal, and someone came to me and said, "Hey Eric, you're presenting the deepest radio maps in the universe. We want to use your map to look for these guys." Well, okay. And this is what we did, because I mean, another tracer of AGN could be radio continuum emission. But before they did it, I also did it with Esteban Orozco, who is a former master student. And we did it after his master, and now his paper is about to be accepted, I hope. We looked for these little red dots in the radio, and we found none. Even after stacking, again, nothing. And the other team, well, I was in the same team, but the other team led by Giovanni Masolari, a PhD student in Italy, they also didn't find anything. In that case, they used GOODS-N 3 and EGS, which are the deepest maps. And we could only derive an upper limit to the radioluminosity, which is around 2 times 10 to the 39 Earth per second. But even with that upper limit, we can try to get some idea about these weird systems. So what Giovanni did was, okay, we know what is the observed radioluminosity. And this is the expected radioluminosity based on scaling relations. Again, using scaling relations of the local universe. These are the local analogs, and you see the upper limit to the radioluminosity here, all of them being scattered along the dispersion of these different scaling relations. And what is surprising is that even though they are within the scatter of this relation, none of them is detected. So what is the probability that the non-detection of any of these galaxies is being driven by the scatter of the correlation? And the probability is too low. So this points towards a scenario in which these galaxies are surely under luminous. Even if you stack your sources, you see that the average data point is, the upper limit here of the average population is below the expected trend. And again, this is, there is another 5 pages of discussion to explain why we don't see radio emission from these galaxies, and this has been explained in the same terms, or the same physical mechanisms that could also explain why we don't see X-ray emission. And we were so happy because, okay, maybe these are weird systems, so we don't detect little red dots. But then, what happens? Okay. But then there was a professor called Luis Felipe Rodriguez who added more complexity to this. Why? So he and his team recently reported two little red dots. And the first one, when I saw it, okay, it makes sense, because he reported a little red dot with a radial luminosity that if you scale this radial luminosity, well, if the flux density to redshift 5 or 6, the inferred radial luminosity will be in agreement with the upper limits, right? Okay, it's too faint to be detected, so okay, right. But then, recently he reported this one, right? This is the J2048, and that one has a luminosity that is 2 orders of magnitude higher. And with that luminosity, we should be able to detect it. And indeed, there is another little red dot, like this is like proper little red dot because it is at redshift 4.6, that this is the only one that has been detected in radio, right? And it has a radial luminosity that should have been detected in the radio map, right? So that makes us wonder what makes a little red dot being radio loud. And I don't think we have enough statistics to address that. So you can say, okay, you may have barriers, or you can have episodic accretion, or agent variability, or whatever. But I think we don't have enough data to fully constrain the puzzling nature of little red dots at the moment. Yeah.
So I got confused. So Luis detected two
Yes.
little red dots, but then you say that there was only one little red dot detected.
Douglas Felipe detected in the local universe, local analogs.
Okay, so it's not appropriately.
It's not the proper, but it kind of gives you an idea of the radioluminosity that you expect to see. But then when you look at this guy, it has a radioluminosity quite similar to the one that Douglas Felipe found. But we do have the sensitivity to detect this type of galaxy.
And what is that? How do you find the analog?
Analog is
This is an analog.
yeah.
How do you know this is an analog of what?
It has the same physical properties, same. So including low mass, low metallicity, the broad diamond H-alpha line profiles, and also they have like a typical V shape. You have a blue spectrum and a red spectrum, so that it looks like reddish. Is that okay? Yeah. Okay. Sorry.
I was thinking, okay, you see it in the local universe. Can you do maybe spectroscopy on how to see if there is something about the physical properties on these particular objects that could help you explain?
I was about to suggest the same thing to Doc Luis Felipe Rodriguez because I was preparing. We had an email exchange like, what can we do with this? I think that's the next thing to do. Like, what makes a difference between these two sources? Again, this is an issue with the statistics, no? But, okay, one-to-one, but at least it gives you an idea. And I did that, at least like looking in the literature, and I found that, for example, the one that Douglas Felipe reported, the brighter one, it also has, I didn't mention it, but it has been detected in the X-ray. So it is also X-ray luminous, and there is some indication of tidal features, right? So pointing towards recent merging, I don't know. So I think that's an excellent suggestion that we should, the leading author should do in the future. Okay. Now, finally, some weird sources that we find. You know, when you write proposals, you say, I want to do this, I want to do that, but then when you get your data, okay, I wasn't expecting this, but thank you. And this is the case for these sources. I mean, it's kind of boring to work with, to inspect all the images individually because you have 3,000. But out of the 3,000, sometimes you get something like this. And something that drew my attention was this one, because you can see that the bright red emission is totally offset from, at least from the brighter optical emission. And you see this kind of tail, or I don't know what is this. And if you were to see, what would you expect to see for a wandering supermassive black hole? Something like that. This looks similar, but It's not that bright, and you don't see like ongoing merging activity. So this could be pointing towards something different, like a bright star forming region or even a supernova explosion. And sometimes you want to get more religious, you get something like this. You get these X-shaped radio sources like a hammer, and I don't know, I wanted to discuss this with Jacopo, Bernardo, Isu. I don't know what it is. You can see like a bunch of galaxies here, it's a weird system. But I think these are case studies to understand how merging activity can trigger both AGN or star formation in the central region. So I'm going to stop here. This is my summary. So if you are interested in using this data, you can just send me an email. So key messages. We have found, based on the radio source count, that some indications of suppressed radio emission in low mass star-forming galaxies. We have seen that it appears that the 1.4 radio luminosity of those low dose star-forming galaxies decreases with redshift, which could be pointed towards inverse Compton losses. The measured radio sizes of star-forming galaxies decrease to the emitted frequency, which has implications on how we want to use radio continuum emission for high redshift studies. And the little red dots, we know nothing yet. So thank you. I will stop here.
Very interesting talk here.
Yeah.
Time for questions. More questions. Yeah, back there, Roberto first, and then Jack.
Given that you already have your detections of the 1 GHz radio, are you planning to do like a targeted survey on the detections to do this experiment of the morphologies star formation rate calibration using 33 GHz continuum that traces jump stars rather than supernova?
So you're saying that you want to use the 1.4 GHz radio luminosity?
No. So to repeat the experiment with higher frequencies, I guess you don't.
Oh, what? Higher
you
frequency?
Don't do it
Yeah.
think of uses more.
Yes.
But given that you already know where the sources
Yeah.
are.
That's an excellent suggestion. That's something that I thought like to do, like what's happening at a completely free regime. Yeah, that's a good suggestion.
So about these little red dots, you focus on the AGN interpretation.
Yeah.
What about purely the opposite, purely star-forming interpretation? So would the X-ray and radio emission be more compatible with this?
Yeah, indeed. The thing is that at the same time, you can explain the X-ray emission and the absence of X-ray and radio emission. How would you explain like the extremely broad line profiles?
Outflows.
Yeah, but those.
Well, I know there was some paper that claim that the broadness, the width of the H alpha or whatever other line can be explained by outflow.
Yes.
But in a subsample of.
Yes, exactly. I think that the consensus will be that this is a heterogeneous population. Because you can have like an AGN, like for example the ones that are detected in radio, and sometimes you can have like probably outflows. I tried to understand the paper by Jerry Matthew last year, and he's claiming that you can explain that with outflows and how you get powerful outflows when you have like this cocoon. So you have like low density regions that and in that particular region it can escape, and you have to be lucky so that you are looking at the right direction so that you can see. So I think that there's still a lot of things to discuss.
Yeah, but if you have so fast outflows, they will naturally explain. You should have X-ray emission. So the question is, if you have the outflows, why don't you have X-ray emission?
What I meant is that not detectable with current data set. So I mean, of course, you will have X-ray and radio emission, but the thing is that we will not detect it with the current data set.
The observations were XMM or Chandra?
No.
The ones that you try to observe eventually?
No, I mean, it's too difficult. So you can see, I don't know if, I don't remember off the top of my head what is the upper limit in X-ray flux, but it is too low. I mean, yeah, it is too low to be detected. There are some papers, at least in radio, I do know that they try to play this game like, what if the little red dot is only powered by star formation and you need NGVLA? And even with the NGVLA, it's going to be difficult. Yeah?
Okay, thank you. I was wondering about in the session when you talked about the stack images that you did not detect anything, and also the other team did not detect anything. Does it mean that you need more observations on that sources, or does it mean that there is nothing?
Yeah, that's the question. Yeah, that's a very good question. So there are two approaches. You either integrate a lot on a single source, but then what if this source is radio quiet? Probably what the best thing to do is to observe a lot of little red dots and stack them so that you get an average. But the thing is, again, like we only have upper limits and we have one detection, so it's difficult to know. I think that's what is exciting now about high-redshift astronomy, that these things are kind of, puzzling. And there are a lot of debates. Some people think that these are like supermassive stars or collapsing black holes, or yeah.
You should ask Luis Felipe where to look at.
Yeah.
Questions here? Anything on Zoom?
Just last comment following on Rogelio's suggestion, you should check on the local volume matter data on your galaxies. They're available for all.
Yeah, that's something that we can. Well, I can help. But yeah, that's a good suggestion, because now with the VLAS, all the sky servicing radio and complementing, there is a lot of synergy with these optical projects. Thanks for the suggestion.
So SKAO is starting operations next year. Is that still
Depending on who.
soon?
I mean, there are some precursors now. Like MIRCAT is delivering nice data. So, but the full thing is in process.
All right. If there are no further questions, let's thank Eric for an interesting talk.